So yesterday we talked about state space representation and we learned the concept how to obtain state variable representation of mechanical systems. So and I discussed few examples. A few more examples are required to be discussed in order to make things more clear. And since it's a very in-depth concept, because space representation or state variable representation is something that you might observe in different books to be implemented differently. So, so it's important how to know that how are you going to implement the state variable representation for a system, and of course you are going to find different variables implemented in different books and in different ways. But if you understand the essence of how you obtain state variable formulation of system, then you can interlink all of them easily. So shown over here is an example again for a mechanical system accompanying two masses. And this example I think had already been done in unit 1, where we were finding the transfer function of systems. So I guess we found the transfer function of this particular system, and if not, so you can do it yourself. But today we are going to discuss how to obtain state variable formulation or state space representation of this system. So suppose in this way we did in case of transfer function, we will obtain the free body diagram of the masses, starting with the mass on which force is applied, which is M2. So after obtaining the free body diagram in this manner, so since in case of M2 you have force applied on the right side, then you have resisting forces existing on the left side on the mass because of spring and because of its inertia. And since the surfaces are frictionless, thus no damping or frictional damping would exist. So this gives the equation which is written as follows. So let's call this equation as 1. So there is nothing new to explain in this particular expression. Things have already been discussed in unit 1. So I expect that none of you should be having problem in obtaining this expression. Now if we try to draw the FPD of mass M1. For mass M1 you have forces which act on this mass and tries to move it because of this spring attached to it. Because mass M2 moved because of the force F, which was the exerting force, and the force because of a spring is resisting for mass M2, but the same force because of a spring will be acting on mass M1, and that too on the right side. So, and the value is the same, the magnitude is same as that in case of the resisting force of mass M2, and the resisting forces that exist are because of the dashpot and the mass. Again, the friction for this mass is also 0, and thus we are not going to talk about the frictional force or the damping because of friction. So we obtain the equation given by 2, and again as I told you that in order to acquire state space representation, is one thing important is that if you look at this particular figure, you see that there are only 3 energy storing elements, namely mass 1, which stores the energy in the form of kinetic. So mass of M1 will be storing the energy in the form of kinetic energy. M2 also will be is capable of storing energy in the form of kinetic energy, while spring K is capable of storing energy in the form of potential because of its expansion and compression. So there are 3 energy storing elements, and by the concept that we learned that if a system has 3 energy storing elements, then it should be having 3 state variables. But for mechanical systems, as I told you yesterday, since whenever you deal with mechanical masses, for any mass, you will be assuming 2 state variables. One is displacement x, the other is velocity. Which means that in this particular example, you will be having displacement x1 for mass m2 and displacement x2 for mass. In fact, this should have been written like x2 here and x1 here, but nevertheless. So in this figure, we have taken displacement x1 for mass m2, x2 for mass m1. So I guess x1 is associated with input applied. That is why we call this x1. Nonetheless, so we have displacement of mass m2, which means that the state variable for mass m2 will be x1 and its velocity, which is x1 dot. The other state variable would be x2 and third state variable would be x2 and its velocity x2 dot. So this is how we try to uh, figure out the number of state variables in case of mechanical system by looking at the masses which are present in the system. But if you look at the energy storing element, it should comprise of only three state variables. So we'll talk about those as well in the next example. But for the time being, we say that it will be having four state variables because for masses we assume two state variable, displacement and velocity. And since you have two masses, then that is why we'll be having four state variables, displacement and velocity corresponding to each mass. This can also be clear from the differential equation that we see here. So if you see equation 1 is a second order differential equation which could be converted into two first order differential equation. Likewise, you obtain equation 2 which is a again a second order differential equation which can again be converted into two first order differential equation. And thus from equation 1 you get two first order differential equation plus two first order differential equation from equation 2. That makes four equations of first order. And thus four equations of first order means that this system will be having four state variables. So there are two ways of knowing how many state variables does the system has. So we discussed both of them. One is the way most of the books say that the best way or the most accurate way for picking the number of state variables is to look into the differential equation associated with the systems. And books also say that by looking into the number of energy storing elements, you can conclude how many state variables it could have. So that again depends upon what situation you're talking about. So for this particular case, most of the books adhere to the concept of assuming displacement and velocity as a state variable for mass, and thus since the system has two masses, we'll be assuming that it has four state variables. And this is also justified by the two differential equations of second order, which gets converted into four differential equations of first order. So we start assuming. So the state variables, and let us assume a1 is equal to x1. In fact, if you get a bit expert in taking out the state variables, then you would skip this step of assuming state variables in any other form. So instead of writing this a1, you would have been writing state variables directly in the form of x1 and x1 dot, x2 and x2 dot. So since we are learning as a beginner, so we'll be assigning certain other names or nomenclatures to the state variables x1, x1 dot, x2, x2 dot. And after you get expert in obtaining the state space representation there, you might like to skip this step and write directly the state variable formulation in terms of these variables x1, x1 dot, x2, x2 dot. So after the assumption of state variables a1, a2, a3, a4, now we'll try to identify the state equations. So state equations will be written always in the form of x dot equal to ax plus bu. So this is a default state, state equation in which you will be writing the state equation in this form. So as you see, you assumed a1, a2, a3, a4 as a state variables, and thus we'll be writing each of these equation in the form of a1 dot equal to something in terms of a1, a2, a3, a4. So you have x1 dot, which is nothing but the vector formulation of the state variables or the state change, like this. So this will be x. This will correspond to x dot. And again for x you will be having the same matrices without the derivatives. So this will become a1, a2, a3, a4. And again I repeat, you will have to mind the order for this vector. So if you are going to choose a1 as the first element, a2 as second, a3 as third, and a4 as fourth element, then you are bound to choose the same order here. So in case if you choose the first element here as A2 or A3 or A4, that would become incorrect. So you won't get right answer. So the order that you're choosing for state change, state variable change, should be same as the order you're choosing here for state variables. Now your duty is to populate the matrix A, and again since this matrix is out of order 4 cross 1, and again this is a matrix of 4 cross 1, which means that the order of matrix A should be 4 from this, and from this it should be 4 cross 4. So you are going to get a matrix A of order 4 cross 4. Likewise, you have input. So input in this case is F. So you'll be writing in place of U as F, and you'll be populating corresponding to matrix B, which will be having an order of 4 cross 1 as well. So let us try to formulate the matrices by populating them. So writing in terms of the state changes, A1 dot gives you, so since you assumed A1 as X1, and thus X1 A1 dot will be X1 dot, so X1 dot is nothing but A2. So we wrote this as A1 dot equal to A2. Likewise, A2 dot will be X1 double dot. So X1 double dot will can be obtained from the equation that you have written from as one. So equation was obtained from the FBD of mass m2, so which was written like this. So from this equation we see that d square x1 by dt square is nothing but x1 double dot, which is a2 dot, and thus this corresponds to a2 dot. So let me write this here. So this term is nothing but a2 dot. So you're going to obtain A2 dot and going to write this in terms of f k x1 x2, and again since x1 x2 had been changed, these are not state variables or input, you will be changing these values. So you assumed x1 as a1, you'll be writing in place of x1 a1 and in place of x2 as a3, since you assumed them here, and thus x2 dot can be written in terms of a1 and a3 in this manner. So a2 dot is input divided by m2 minus k upon m2, which is nothing constant, and into a1 minus a3. So this becomes equation B. Likewise, this third step is state change a3 dot, which is nothing but x2 dot, and x2 dot is nothing but a4. So thus we can write a3 dot as equal to a4. Likewise, a4 dot is nothing but x2 double dot. So it's clear from equation 2, you have d square by dt square x2, which is nothing but x2 double dot, or a4 dot. So a4 dot can be obtained from equation 2 in terms of the state variables in place of x1. So this is a4 dot, while x1 can again be written as a1 and x2 will be written as a3, while dx2 by dt can be written as, so you are going, since you have already written a state change, you have already chosen a state change corresponding to this term, and thus you will avoid any other variable, any other state variable change other place. So since you choose a4 dot here, you won't be choosing any dot or d by dt here. So x2 dot corresponds to a4. So you'll be writing this as a4, simply a4. You can write this as a3 dot, but this would become incorrect because you are required to find only one state change, and you already wrote a state change a4 dot. That is why this a3 dot is not required anymore. So a4 dot can be written in terms of variables a1, a3, a4. So this is from A to D, you get the state equations, and then you're going to use these equations to formulate the state array. So you're going to get the matrix A and B as well using these equations from A to D. Now there are output in this system in the form of displacement x1, x2. So since the output were not mentioned in the question, so you can assume that the displacement x1 and x2 both are taken as output. So in some questions it might be mentioned that take velocity as output. In that case, you are going to take output y1 as x1 dot and not as x1. If the question mentions that the output is displacement, then you are going to choose y as x1. But if the question mentions to choose the velocity, the output as velocity, in that case you're going to choose output y1 as v1, and which is nothing but x1 dot, and output y2 as x2 dot, which is the v2. So from here we move forward. So using the equations that we just obtained, we are going to populate the matrix A. So we have written the state change x dot. So this is nothing but x dot. This becomes the matrix A. This is x. This is matrix B, and this is input U. So input is nothing but the force which is applied to mass M2. So now this will be clear that what order of A should be this matrix B. So this should be 4 cross 4 because you have 4 cross 1 here, 4 cross 1 here, and only a 4 cross 4 matrix will be multiplied by 4 cross 1 matrix to give you an answer of a 4 cross 1 matrix. Again, you should be having a matrix B of the order 4 cross 1, and if you populate these matrices, then what you get using the equations that you just obtained. So on looking equation, the first equation, a1 dot is equal to a2. So a1 dot should be equal to a2, and you don't have any expression for a1, a3, a4 as well as f, and thus you are going to populate this as 0 multiplied by a1, 1 multiplied by a2, since you have a1 dot equal to a2 and a3 is not present, thus 0, a4 is not present, again 0, and input is not present, again 0. a2 dot from equation 2 can be written in terms of a1 as minus k by m2, and since there is no term for a2, 0, and again minus a3 multiplied by minus k by m2 plus k by m2, and for a4 you don't have any term, this is 0, and for input you have 1 upon m2. Then a3 dot is equal to a4, so this becomes 0, 0, 0, 1, and no input, 0. a4 dot is k by m1, a1, no term for a2, 0. a3 is k by m1 with a minus sign, and again minus b by m1 with a4, and no input, 0. So this is the required state equation, and for output equation, since y1 is assumed to be equal to x1 and y2 is x2, so it's not important that it's not necessary that you choose y1 as x1. You can choose y1 as x2 or y2 as x1. So it all depends on you. The order will change, but the answer is fine with both. So since a1 was chosen to be x1, we assume this as a state variable corresponding to x1, and x1 is nothing but y1, and thus y1 is equal to a1. Thus this will become 1, and the remaining terms are 0. And again, since there is no term of f here, you have 0. Then again y2 is equal to x2, displacement of mass m2, which is nothing but a3, the state variable a3, and thus y2 will be written as 0, 0, 1, 0, and 0. So this is the required state space representation or state variable formulation for the given system, where this corresponds to the state equation and this corresponds to the output equation, and they both collectively are termed as state variable formulation or state space representation. Likewise, as I told you that books have assumed systems like this to have 4 state variables, but still there exist some references which say it should be having 3 state variables. So I've taken the solution. I'm going to talk about the same as well, but this is only possible if you take output as velocity. In this case, in the previous case, You could have taken output as velocity. For example, y1 could have been written as x1 dot instead of x1. Likewise, y2 would have written as velocity v2 or x2 dot. So in such cases, since x1 dot is nothing but a2 and x2 dot is nothing but a4, and thus y1 can be written in terms of a2. So instead of writing 1 here, you would have written 0 and 1 here. Likewise, y2 would have been 0, 0, 0 and 1 here. So this matrix A corresponds to output which are velocity, while the previous matrix, this one, corresponds to output taken as displacement. So you can choose output as velocity as well if it's not mentioned in the question. So now I present the solution if you have to choose output only as velocity. So this solution that we will discuss does not holds for output taken as displacement. So the good part of this solution is that because we learned that for any system there should be a minimum number of state variables. So the question that we just did had 4 state variables, despite that it was having 3 energy storing elements. But this question now, the same question, and we will be choosing only 3 state variables, and this can be only solved if you are going to choose output as velocity and not displacement, and that will be clarified when I come to the final answer. So again, drawing the FPD, obtaining the equations for both the cases. So these are the equations. So this is the FPD of M1. This is the equation. Again, assuming state variables. Now we choose the state variable S1 as x1 minus x2 and not as x1. Since we saw that spring has both its ends moving with different displacement, this one moves with the displacement x1 while this moves with the displacement x2, and the energy that is being stored in energy in the spring is proportional to x1 minus x2. Since we are talking in terms of the number of energy storing elements, so we got this from the energy being stored in the spring, while x1 dot comes from the velocity of mass m2. So since mass, when it is moving with certain velocity, is stores energy in the form of kinetic. So you have half mv square, which is kinetic energy, and thus we choose v1 as the state variable. Likewise, v2 is chosen as state variable, which corresponds to the kinetic energy portrayed by mass m1 moving with velocity x2 dot or v2. So we are now trying to choose the state variables corresponding to the energy storing elements in the system. So in such a case, now we get S1 dot, the state change will be equal to x1 dot minus x2 dot. So x1 dot is nothing but S2 and x2 dot is nothing but S3. So S1 dot becomes equal to S2 minus S3 here. Likewise, S2 dot is obtained from equation 1, this equation, and you see that x1 double dot, which is S2 dot, will be written as this, and likewise S3 dot is x2 double dot, which can be obtained from equation 2 like this. So these are the 3 equations, and we are going to change. So first of all, we will verify that each of these state changes are written in terms of state variables and or input or not. So since we see there are variables only corresponding to state variables and no other variables apart from state variables or input, and thus we will proceed to populate the matrix A. So using these expressions again, you will populate matrix A, x1 dot, x2 dot, x3 dot, and you have s1 dot equal to s2 minus s3, so this becomes 0, 1 minus 1, s2 dot equal to minus k by m2 s1, it's written here 0, 0, f upon m2, 1 upon m2 times f, s3 dot is k upon m1, no term for s2, 0, minus b by m1, s3, 0. And now since you'll get the idea why we choose this works only for output taken as velocity. The reason is that if you are going to choose output v1 variable output of y1, we have taken in place of y1 v1 here. If you're going to choose this as displacement x1, since you don't have any since you're choosing the state variable s1 in the form of x1 minus x2, and you see that the state variables s1, s2, s3 can by any means cannot be written in terms of x1. So you cannot obtain x1 in terms of s1 or s2 or s3 or their combination anyhow without avoiding the derivatives. So you are you must try to obtain this in terms of linear dependencies with s1, s2, or s3, the state variables. Then and only then you're going to formulate the output equation. But we see that V1 cannot be obtained in terms of the displacement cannot be obtained in terms of S1, S2, S3, and that is why you cannot formulate the output equation when you take displacement as output. But if you take velocity of each of these masses as output, then velocity for mass uh, m1, which is v1. So if you say this is v1 velocity, the mass m1 moves. So sorry, v1 corresponds to the velocity of mass m2, and this is v2. So if you say that velocity of mass m2 is v1, or v1 is nothing but x1 dot, and since x1 dot is nothing but s2, so v1 can be written in terms of s2 like this, and likewise v2, which is the velocity of mass m1, and is equal to x2 dot, and x2 dot is written here equal to s3, and that is why v2 can only be written in terms of s3. So this is a limitation with this approach. If you're going to choose the minimum of all the state variables, then you are bound not to choose displacement as output. So you are left with either velocity to be chosen as output. Now, with this knowledge that we learned for electrical and mechanical systems, we'll try to model a separately excited DC motor in a state variable form. So you learn how to obtain the transfer function, the block diagram, the signal flow graph of this case, of this motor. And now we'll try to obtain the state space representation. And it's very simple because if you remember the mathematical formulation that we did for this separately excited DC motors in unit 1. So we're going to use the same equations to obtain the state space representation, and I'm not going to talk about the the application of KVL, KCL or Newton's law to each of these elements shown, and since we have already been studying this in unit 1, so I'll be straightforward writing each of the equations. First of all, you will have to identify how many state variables does the system have. So for electrical system, so one reference or the book mentioned that for electrical systems, you will always look for the number of energy storing elements in order to know the state variable. So this is going to be always true. You will adhere to it instead of thinking of the differential equation. So you will always get the order of differential equation in electrical network equal to the number of energy storing elements. So if you talk about the electrical circuit here, so in this circuit you have one energy storing element which is inductor, and thus this will give you a state variable. And in what form? So we choose for inductor state variable IL. So if you remember the electrical circuit that we saw. And again we have the second part in the form of mechanical term comprising of a mass with moment of inertia J. So applying the same concept of choosing state variables, for this mass we will be having state variables in the form of displacement and velocity. So since it's a rotational system, you will be having angular displacement theta and theta dot, which is omega. So these will be two state variables for mechanical system. So we have in total three state variables, IL, theta and omega for the system. Since energy storing elements are inductor and mass, we recall the equations that we saw in unit 1. So this was the equation that we obtained. So and then equation 2 was written after applying KVL. So I am not going to discuss how we obtain this equation. This has already been discussed in unit 1, and if you want to revise it, you can refer to the lecture that had been uploaded. Now we take the state variables as I, L, theta and omega. In fact, this should be small I. Small I. theta and omega, since all of them are in time domain. So we obtain the first state change, theta dot equal to omega. Then we have omega dot, which is obtained from equation A. So this part contributes omega dot, which is since this is angular acceleration, which can be written as omega dot, and this is omega. So omega dot will be written in terms of state variables theta, omega, and Ia, and no other variable. So we see that Ia is here, omega is here. So this becomes equation 2. And again from equation B, so you write Ia state change in terms of minus RA LA Ia minus EB plus 1 upon LA VI. Now we see that this state change Ia, the third variable, state variable Ia, its state change is written in terms of state variable Ia and VI. VI is input, while Ia is the state variable. But EB is not the state variable. So what should we write in place of EB? So a correct answer from your side gets a bonus mark. What should be written in place of EB? I repeat my question, since you have Ia dash written in terms of state variable Ia, you have input VI, but you have another term EB, which is neither state variable nor an input. So what should we do for EB? Since I told you that back EMF EB is proportional to what? It's proportional to velocity, angular velocity omega. So back EMF is large when your rotational speed is large, and it will be small if your motor is rotating at a lower speed. So if you remember the expression for EB, since it's proportional to omega, you can simply say that EB is equal to K times omega, and the correct formulation was KB d theta by dt. So this was already discussed in unit 1. So this is nothing but this part is omega. So and thus you can substitute the value of EB by writing this as KB times omega like this. So you get Ia dot equal to, oh, I missed LA here, so this should be EB by LA. So now we see that this equation, the state change for Ia dot is written in terms of state variable Ia, another state variable omega, and the input Vi, and thus this can help in formulating the matrix A and B. So from equation 1, 2, and 3, so what were 1 and 2? Equation 1 is this, equation 2 is this, and we get equation 3 as this. So using these three equations, we formulate matrix A and B. So if you use 1 and 2, so since theta dot is equal to omega, this can be written as 0, 1, 0. And since there was no part of input, this is written as 0. Omega dot was written as 0 minus d by j times of omega, and kt by j times of Ia with 0 input. And Ia dot from equation 3 can be written as 0 minus kb by La minus Ra by La Ia, and the input multiplied by 1 upon La. And the output can be expressed since we have chosen output as angular displacement theta, and you can, if you like, you can choose omega, which is the angular velocity, as output as well, but for the time being we are going to choose theta as output. This can be written as 1, 0, 0, 0. So this is the required state variable formulation, a state space representation of the separately excited DC motor. And if you in case have any doubt for the lecture that had been taken today or previously, you can ask me questions.